Good morning, friends. Now we can see our chapter number 12, Electromagnetic Induction. In this chapter, we can study our new topics, Faraday Law of Electromagnetic Induction. Now, the first law of electromagnetic induction is whenever there is a change of magnetic flux in a closed circuit, an induced EMF is produced in the circuit. The second law of electromagnetic induction is the magnitude of induced EMF produces in the circuit is directly proportional to the rate of change of magnetic flux linked with the circuit. Then, if phi is the electromagnetic flux linked with the coil at any instant of t, then induced EMF, that is E, is directly proportional to d phi by dt. Then we can get the equation E is equal to k d phi by dt. Here if E, phi and t are measured in the same system of the units, then the k is the constant, it's equal to 1. Then we can get the equation E is equal to d phi by dt. If we combine this expression with the first law, then we can get E is equal to minus d phi by dt. For a coil which is consist of number of turns of is E is equal to minus n d phi by dt. Now the flux rules, according to which the electromotive force is equal to the rate at which the magnetic flux through a conducting circuit is changing. Therefore, the SI unit of E is nothing but to the Weber per second. Now we can see our next topics, Lenz law. The directions of induced current in a circuit is such that the magnetic field produced by the induced current oppose the change in the magnetic flux that induce the current. The directions of induced EMF is same that of induced current. In short, the induced EMF tends to set up a current, the actions of which oppose the change that cause each. Now we can see the applications of Lenz law. There are first points, motion of the magnet toward a loop. As the end pole of magnet is moved toward the loop, loop's north pole must face the approaching north pole of the magnet so as to repel it. It is as shown in figure. According to the curl right hand rule, induced current in the loop will be counter-clockwise directions. If the magnet is pulled, the loop will have a south pole facing the retreating north pole and will approach the treat by attracting it. The induced current in the loop will now flow in clockwise directions. It is as shown in the figures. Now our next points are energy conversion in Lenz law. The direction of the thrust exerted on the conductors, that is wire, by the magnetic field is opposite to the directions of its motions and thus oppose the motion of the conductor. The currents set up a magnetic field opposite to the original magnetic field. If this field is increasing but in the same direction as the original field, if the field is decreases, the induced current once started flowing in the loop would keep increasing indefinitely, producing joule heating at no extra cost and thus be self-sustaining. Now the Lenz law states that every effect of induction act in opposition to cause that produce it. Now we can see Lenz law and Faraday law. Consider a vector A of the loop which is perpendicular to the plane of the loop. It is flux and oriented parallel. That means the angle theta is equal to 0 to the magnetic field vector B. Then the magnetic field increases with time. By using the definition of the flux, the Faraday law can be written as E is equal to minus d phi by dt. Here we can put the value of phi. Therefore minus d in brackets of vector B into vector A. A is nothing but to the area of the vector upon gt. Therefore area of the vector, it is in mod of. Therefore we can get equation minus mod of A into d mod of vector B upon gt. Here the negative sign in the equation incorporates Lenz law into the Faraday's law. Now we can see our next topic, flux of the field. Suppose the element of area, that is small element dA or area dA, is situated in a magnetic field B. The flux of B through the area dA. Therefore we can get equation d phi is equal to vector B into vector small dA. Therefore we can write down here mod of vector B into mod of vector small dA into cos theta angle. Therefore consider a finite area x vector. The magnetic field vector B will not be the same at different points within the finite area. Calculate the flux over each section and then to integrate over the entire area. Therefore we can get the equation phi is equal to integration of vector B dot vector dA. If the magnetic field at every point changes with time as well, then the flux phi will also change with the time. Therefore we can write the equation E is equal to minus d phi upon dt is equal to minus d upon dt integrations of vector B into bracket of t into dA. This is the flux of the field.